In this video, we will start our next chapter, Continuous Functions on Topological Spaces. First, I will introduce the definitions in an easier way to remember, and then I will prove the theorems while solving the questions. So let's get started. The first one is homeomorphism. Homeomorphism is a function f between two topological spaces xt to yt dashed. Okay, such that f is bijective, this first condition, and f and f inverse both are continuous, This is definition of homeomorphism. Second definition is direct. This sign is a relation, is a binary relation on D, is said to be a direct if this relation is transitive, that means for any m and p in D, m greater or equal to n and n greater or equal to p means m greater or equal to p. Second, this relation is reflexive, that means for any m belonging to D, m greater or equal to m. And the third one is for any mn belonging to D, there exists some p which is greater than both m and n. If these all conditions are satisfied, this relation is said to be a direct on D. Next definition. Net. Net is also a function. Let D and this relation greater or equal to is a directed set. Which means this relation is a direct on the set D, and net is a function from D greater or equal to a non-empty set X. This function is simply called a net. Okay, X not equal to phi. Now take an example. Since we know that the set natural number is also a directed set, right? This is also a directed set. Directed set does not necessarily have to be a partial ordered set. Okay, so this is a directed set simply. So any sequence forms a net on this directed set, right? Now next definition. Filter. A filter is a family F on a topological space xt that satisfies these three conditions. First one is if A belonging to F and A is contained in B, then B is contained in F. That means let this be a family of subsets of X. This be an arbitrary family. If any of this subsets is contained in F, that means the rest of its supersets will also belong to F. Okay. Second condition is let A be belonging to F, then their intersection will also belong to F. Third one is phi does not belong to F. If phi belongs to F, then every set is a superset of phi, then every subset of X has to belong F. But this is not always possible, right? So phi does not belong to F. Now, do you know what does it mean by the term a function is eventually in a set? Take this be a set X and this be a net or a function. Okay, this net is eventually in this set X. Why? Because after some finite number of points, all the rest of the points of this net lies in the set X. Okay? So this function fx is eventually in the set X. Now take this as a note that let this be a net where n belongs to D and this relation. Okay, this be a net. This is said to be convergent to a point U belonging to X if for every neighborhood nx of X, this net is eventually in the set nx for every neighborhood. Now the second note is about filter. A filter f is said to converge to a point U if for every neighborhood nu of U, nu is a member of f. Okay, then the filter is said to converge to U. Our first question says, give an example of a mapping from a topological space to another which is open and continuous but is not closed. This is a 2 marks question. Now let f be a function f defined on a topological space x tau to x tau, where x is closed 0 to infinity and tau is standard topology on this set X. Okay, so tau is generated by this set AB, where AB both belongs to R plus union 0, right? So we have to find a function f such that f is continuous and open but not closed. Okay, so if we take this function fx is equal to x over 1 plus x, since x belongs to the set X, capital X, so x must be non-negative. So for any value of x, this is less than 1, right? This is less than 1. So f image of this set X always lies between of this set is 0 to 1, closed 0 to open 1. Okay, so now this set is this function is obviously a continuous function, but we have to show that this function is open also. Okay, so if we take any open set AB, f will take this open set to another open set. How? Since this function is monotone, so this interval, this open interval is mapped into another open interval, which is some a over 1 plus a to b over 1 plus b, something like this, right? So f image of this open interval is also an open interval in x tau, but there exists at least one closed set in x tau which is not mapped into a closed set. If we take 0 to infinity, that means x itself. So x is a closed set in x, right? But this set is mapped to 0 to 1, which is an open set in x tau. Why this is an open and not semi-open? Because x is starting from closed 0 and ending and going up to infinity. But this is an open set because but this is not a closed set actually, because 1 is a limit point of this f image of x, but one does not lie in here. So this function takes open sets to open sets, but not the closed sets to closed sets. Okay, so this problem is done. Next question, define a filter and prove that a function f from x tau 1 to y tau 2 is continuous at x is equal to c belonging to capital X. If and only if for every filter f in x which converges to c, f of capital F converges to fc. I have already given an idea about what does it mean when we say that a filter converges to some point in the beginning. Okay, so and already discussed what a filter is, so we will skip to the second part of the question. Let us assume the function f is continuous. Let us assume that f is continuous. And for x is equal to c belonging to capital X, there exists a filter that converges to c. Now we need to prove that f of capital F, that is f image of capital F, converges to fc. We have to prove this. Now what does continuity means? Let this be the topological space X and this be Y, then let this be f image of X, which is a subset of Y. So there must be some f of c. This is f of c. Now since f is continuous, so we can say for every neighborhood, we call this as n of fc. This point is fc, so this neighborhood is n of fc. For every neighborhood n of fc, there must be some neighborhood which we call n of c, such that the f image of this n of c is contained in this. This is the f image of n of c. This region is the f image. Now since f is a filter which converges to x, we let n of fc be any neighborhood of fc. Okay. Then by continuity we can say f inverse n of fc. If this is n of fc, there must be some f inverse n of fc, right? So f inverse n of fc is a neighborhood of c in x, and the filter capital F converges to c means every neighborhood of c is an element of f. That means this is an element of f inverse n of fc being a neighborhood of c belongs to f, the filter. So it must be equal to some, this element must be equal to some f1 that lies in capital F, which implies that n of fc belongs to f image of capital F, right? So f image of the filter f also forms a filter in Y. We have to show that this f image of the filter f converges to f of c, right? So now since for every neighborhood n of fc, every neighborhood n of fc belongs to this filter in Y, that means this filter converges to fc. This filter converges to f of c. Now to prove the converse, which is for every filter f in X that converges to C, f image of f converges to Fc, we need to show that f is constant. Okay, so we take that whenever there is a filter f in X that converges to C, whenever f of f converges to Fc. This is in our hands, so we have to prove that f is constant. Okay, f is continuous. Okay, so and we will prove this by showing some contradiction. So if possible, let f is not continuous, f be not continuous. Okay, so since if f is continuous, then for every neighborhood n of Fc, f inverse n of Fc must be a neighborhood of C. Since we have assumed that f is not continuous, so there must be some neighborhood nc of C such that there exists some neighborhood nc such that nc is not contained in f inverse n of Fc. There exists some neighborhood. Okay, so f of nc is also not contained in n of Fc, which implies that n of Fc does not belong to f of f. Why? Because f is a filter which converges to C, and for which f image of f converges to Fc, and n of Fc is a neighborhood of Fc which does not belong to f image of f. It shows that f image of f does not converge to Fc. So this is a contradiction, because if filter converges to a point, then every neighborhood of that point every neighborhood of that point have to belong to that filter. But this neighborhood does not belong to this filter. This contradicts that this filter converges to Fc. So this is a contradiction. So our assumption is wrong. Our assumption was f is not continuous. So this one is wrong. Hence f is continuous. Now this video has already become lengthy, so I will upload the rest of the problems in this topic in my next video. Keep watching and subscribe. Thank you.